So good afternoon, everyone, and welcome to the 6th of the 13 webinars that are part of the 2020 EMOS webinars program. My name is Caterina Giusti. I'm professor of statistics at the University of Pisa in Italy, and today I will act as the webinar facilitator. As this is a live event, I would like to specify that today I'm connected from my house, as all the other members of the EMO staff to the University of Pisa, as our speaker, and I guess also as many of you. It is fundamental that we all follow the direction of our governments and organizations. And for the EMOS events, I think that we are lucky, since webinars are indeed a powerful tool that we can continue to use also in these difficult times. So going back now to our webinar, let me first explain for any newcomers that EMOS stands for the European Master in Official Statistics, a joint project of universities and data producers in the EU member states, EFTA and EU candidate countries. If your university is interested in applying for the EMOS label, please consider that a permanently open call for universities is available on the EMOS dedicated page on the Eurostat website. For staying in contact with the EMOS news and community, please follow the EMOS on Twitter. The EMOS account is @EU_EMOS. Now, before I give the floor to our speaker, let me first briefly explain how we run the webinar today. As a participant, you can watch and listen to the session. To interact with the presenter, you can use the chat represented by the comic symbol. We encourage you to prepare your questions and pose them during the presentation or the question breaks. We will have a couple of question breaks and then the final discussion to reply to your questions. Should you have any technical problem, please try restarting your Skype for Business on the computer or device that you are using. For more specific technical questions, you can use the chat and you will receive a personal reply. In any case, please consider that the slides of the presentation are already available on the EMOS 2020 events website, and the link is also available in the chat. So today, I have the great pleasure to host Edwin de Jonge from Statistics Netherlands. Edwin is a methodologist and data scientist at the R&D department of CBS, Statistics Netherlands, the Central Bureau of Official Statistics in Netherlands. Having a background in computational physics, his research interests include statistical computing, data visualization, and complexity sciences. He is an author of the book Statistical Data Cleaning with Application in R, and has published papers and packages on data cleaning, data visualization, and mobile phone analysis. Today, he will present about the communication of uncertainty in official statistics. So, Edwin, the floor now is yours until the first question break.
Okay. Thank you, Caterina. Well, good afternoon, everybody. Caterina introduced me, so let's start with the webinar. Today we're going to talk about communication of uncertainty in official statistics. So Caterina did the honor to introduce me, so I can skip this one. So first, let's start with statistics. So if you look up statistics in Wikipedia, you will find quite a big lemma. But it begins with: statistics is a branch of mathematics dealing with data collection, organization, analysis, interpretation, and presentation. And what you can see is that official statistics institutes do all of these 5 things: so data collection, organization, analysis, interpretation, and presentation. And contrary to what you learn in university or high school, most statistical actions are not in analysis, but in the other 4. So collection takes a big part, organizing your data takes a big part, and also interpretation and presentation are very important for doing official statistics. So when you're doing, so this is the start of the lemma of statistics. If you look, oh, did you?
Now we can hear you.
Okay.
Yeah.
So if you look at in the Wikipedia, you will find the lemma statistics, and our national statistical institutes spend a lot of time in doing data collection, organizing data, doing the analysis, interpreting the data, and also present it. Also on this Wikipedia page is statistics is concerned with the use of the data in the context of uncertainty and decision making in the face of uncertainty. So why we are producing the statistics, these official statistics, is to give decision makers and policy makers the ability to use these numbers to influence their policies, or to use them in their model or in prediction, or etc. And one very important part of statistics is that it's in the context of uncertainty. So it's when it's needed for decision making, we should accompany the data with uncertainty measures. It's also nice to look at a different perspective of statistics. So a different definition phrased by Cosmos Chalitzi, who's a professor of statistics in the United States. Says statistics is the science which uses mathematics to study and improve ways of drawing reliable inferences from incomplete, noisy, corrupt, irreproducible, and otherwise imperfect data. So he puts a lot of focus on the data quality. So it's incomplete, it's noisy, it's corrupt, irreproducible, and otherwise imperfect. So we should be aware, even when producing official statistics, that our data is not as good as we would like it to be. And we should also communicate this to our audience. So this is what the webinar is about. So uncertainty is part of making statistics, and we all know that. But is it also true for official statistics? And when doing official statistics, we have the benefit of having quite a large population. So you might think that the sampling error is not that big, because our population is big. So let's look at two use cases within our own office, so in the Office of Statistics Netherlands. So why is uncertainty important for official statistics? Well, at least for two reasons. So one is communicating the accuracy, so how precise are our numbers. And the other thing is there's also some inherent uncertainty, and we should be aware of that. So let's view two cases of Statistics Netherlands. So let's look at, for example, the incidence of diabetes. So how many people are suffering from diabetes? In Statistics Netherlands, this is based on a large health survey, which is done annually, so each year. And we can use this to look at how healthy our population is. So, for example, if we look at this graph, which is a bit of old data, so it's from 2001 to 2009, we can see that the incidence of diabetes runs from 2.8 to 4.1 for the whole population. So let's dive a bit more into this. So one thing to look into is we could split this into groups. So this is for the whole population, so 2.8% till 4.1%. If you dive into this, we can split this in small groups. So for example, different age groups. So the columns are different age groups. So the first column is 0 to 25 years old, then 25 years to 35 years old, 35 to 45 years old. The fourth column is 45 to 55 years old, 55 to 65 years old, and then 65 to 75 and 75 plus years old. And the top row is the male population, and the bottom row is the female population. So if you look in these small groups, you can see that the number is quite different for the certain age groups. So while for the total population, the number ran from 2.8 to 4.1, for the different age groups, it's a totally different story. You can see from this picture that diabetes is age-related. So you can see for all age groups the number is rising. But you can also see something different. And that is that, for example, for the older age groups, you can see that the number fluctuates quite a lot. For example, if you look at the age groups 65 to 75, you can see that the number fluctuates between 8% and 16%, which is quite a lot, and which is a bit strange if you think that these numbers should represent the whole population. And it's even worse for the 75 plus. So what's happening over here? And these are actual numbers we produced in Statistics Netherlands. So what's happening is that we're reaching the measurement accuracy. So while these numbers are based on quite a large health survey, we are reaching measurement accuracy because these age groups are quite small. So when you make the group smaller and smaller, you will reach your measurement accuracy, and your groups will get less and less. So you should be aware of the accuracy of your numbers. So one of the things is that in official statistics, there's always, each number we produce is a bit imprecise. And when we zoom into small population, this number gets more imprecise. That's the main message. And we are aware of it, but if you visualize this, it becomes very apparent, such as this example. Another example is with traffic fatalities. So this is the number of people dying from traffic, and this was declining, luckily, from 1996 to 2011. Nowadays it's a bit increasing because of the electric bikes. And the nice thing of this is these are no estimations. So these are based on a register for mortality figures, and these are almost exact, meaning that these are based on how people are registered where they died from. So there's no estimation process going on. So while the previous example is based on a survey and on a sample of the population, this one is the total number of people dying in traffic. So let's do the same trick, not in age groups, but let's split this into regions, for example. So if we split this into smaller regions, you can see for some provinces that the number fluctuates quite a lot. So for example, in the first region, you can see that the number goes up and down and up and down. Some of these fluctuations are more than 10% year-on-year changes. And these are just measured. So this kind of error is not a measurement error or a measurement precision thing, but it's more a stochastic uncertainty thing going on in our data. And again, we should be aware of that, because this indicates it's not that in these regions have become more unsafe from one year to another year. There's a stochastic process going on in these regions, and you should be aware of that again. So this second case is more about stochastic uncertainty. So some of our data have measurement errors or processing errors, and some of our data have inherent uncertainty. In both of these cases, you would like to accompany the data with uncertainty measures, because when they are used by policymakers or by scientists or by the general public, they should be aware that these numbers are estimations, or that they are the result of a stochastic process. So you can frame these types of uncertainty types in two ways. So one type of uncertainty results from the measurement process. So there is a true value of what you try to measure, but due to lack of knowledge, or due to measurement errors, or due to estimation errors, or due to processing errors, or due to conceptual errors, you're not measuring the thing you would like to measure. So there is an imprecise measurement. So that's good to know. In official statistics, there is also, for some of our official statistics, this has also a different flavor. So, for example, in economic statistics, for example, GDP, so the gross domestic product, has different versions of numbers. So for quarterly figures, they will be available in different flavors. So we have a preliminary version, for example, or a final version, and revised versions. And these different versions of the numbers are based on that more knowledge is available. So the preliminary figures are fast, can be produced within a quarter since the previous quarter, and the final ones, or the revised versions, take some more time. But this is all about estimating, about measuring. And the other uncertainty type can be about prediction. So as official statistics, we do not do many predictions. In some areas we do. So for example, population predictions, in statistics analysis we do that. And then there's no true value yet because the future is uncertain, but there's still an uncertainty. So that's a different type of uncertainty, prediction uncertainty. So I would like to know if there's somebody has some questions until now.
Yes, please. If you have questions on this first part, you can use the chat. Of course, this was just maybe the introduction. Otherwise, we go on to the next set of slides.
Specific.
Yeah, I have a specific question about robustness. A long time. Let's see. Yeah, I think you can try. Maybe Edwin. Yeah, we can still decide to reply maybe at the end. But
yeah,
please,
sure.
Yeah, pose your question. Oh. Okay, so we have another question in the middle, but yeah, Joao is, so I have a small region with about 3 points sample, and then maybe we wait.
So is the question about when you should stop communicating, when you should stop with publishing numbers because the support is too low, or?
Oh, yeah, he's saying this is monthly. How can I ensure that the measurement is robust across time?
Yeah, that's a very difficult question. It's more about estimation, and I don't know the details of your specific problem, so I'm afraid I cannot answer it in detail right now. But it really depends on. It's not a sample. Yeah, well, that's quite similar to the previous example where we did it's a bit similar to what we saw before with the traffic fatalities of casualties. there's an underlying process going on, and you could model this, or you could publish both the measured numbers and a smoothed version or a trended version of that. That's one quick answer to this question.
Yeah, okay. So the question was that it was not about the sample, but was the whole population.
Yeah.
And then we have another one, how to communicate intrinsic uncertainty different than error profile of estimate.
Yeah, that's a really good question. And I don't have a real answer to this right now. Most of the times this is done verbally. So most of the times so with the previous example with the traffic fatalities, this would be done in the text accompanying the statistics. So there would be a small explanation why why there are so many fluctuations in the data.
Okay, thank you. So maybe I think we can go on.
Yeah, let's continue.
Yeah.
So the important message is that uncertainty should be communicated, because communication of uncertainty is of importance. So because decision makers are basing their decisions on our numbers or on official statistics, they should be made aware that some of these numbers are more precise than others. And they, of course, notice that these numbers are just guesstimations, but it would be nice to have an indication of how certain we are about these numbers. The strange thing is that if you look into the practices of our official statistics institutes, so most of them are very careful or prudent or reluctant on publishing uncertainty margins. So they are available on websites, but they're quite difficult to find. So that's a bit strange, because uncertainty is very important for statistics, but if you look at our websites of our official statistics, it's very difficult to find uncertainty measures. So that's a bit of a paradox. So there can be quite some reasons for this. So there are a bit of a possible. So one reason could be that most users don't understand them, or most users don't need them. That could be reasons. And these two reasons we will look into furthermore in the presentation or in the webinar. Another reason could be that users may shop with the numbers, so they may choose the number that best fits them, so more a political reason. So instead of having just one figure or number, they could have a range of numbers. They could choose the maximum or the minimum version of the value they would have to like, that they like. Could also be a technical reason, so that as an official statistics office we don't have an accurate estimation of the accuracy. So for some processes it's quite difficult to have an estimation of the accuracy itself. We know about sampling errors, that's quite easy to do. But some statistical measurements are really complicated and can have very complicated errors. So in some cases it's really difficult, but it's more technical explanation. So why it's not possible to do this. And another reason could be that users might lose confidence in the statistical institute. So that's more that we as a statistical institute really like to give numbers, but they are less exact than our users think they are. So we might be afraid that they lose confidence in our institutes. So that could also be reasons that these measurements are, or these uncertainty measures are not available on websites. If you look into communication of uncertainty, so we will go into some of these later on. If you look into communication of uncertainty, there are 3 different ways to do this. So one is verbal communication of uncertainty, one is numerical, and the last one is visual. And the last one is the most promising, so we will look into this a bit more. So verbal communication of uncertainty is not very common in official statistics. And that's because most verbal terms are more on, talk about probability or prediction. And since most official statistics are not predictions but more measurements, they're not really directly useful for official statistics. And it's also a bit difficult to find some common terms on verbal terms. So there are a couple of lists you can find, and one most known is from the IPCC, so the Commission on Climate Change. And since they do a lot of predictions, and these predictions should be communicated quite well, they have compiled a list of verbal uncertainty terms. So their list is virtually certain, very likely, likely, about as likely as not, unlikely, very unlikely, and exceptionally unlikely. And you can see this range runs from less than 1%, 1 to 10%, 10 to a third, third to 2/3, 2/3 to 90%, 90% to 99%, and above 99%. So this scale, so there are a couple of things you could remark on this, can comment on this scale. First, it's not a linear scale, but it's more a skewed scale. That's one. And these are all about probabilities, not about measurements. So numerical communication on uncertainty is most often used in official statistics. And typically these are standard errors of the measurement in our data. And most often these are sampling errors. So when they are reported, most often the numbers that are reported, or the error measurements, the error measures that are reported are standard errors. So from the sampling errors. And most of the times other measurement errors are not taken into account. There are exceptions, of course, but that's most of the case. Most of the case, a 95% confidence interval is used, and often the accuracy is expressed in percentages of the statistic itself. So there's something like the number of the error in this statistic is 1%, something like that. So there is a good practice in communicating numerical uncertainty, and the good practice is that you should express the uncertainty as an interval. So, for example, economic growth is 1.5%, and you could give the interval that it runs from 1.3 to 1.7%. So this is a good practice because for most users, this is really useful because they know the number is somewhere in between 0.3 and 0.7. This is a better practice than doing what you often encounter, is that, for example, economic growth is 0.5 plus or minus 0.2. Well, it's identical, of course, with the first version. A user has to calculate the boundaries him or herself, and that's less direct. So it's better to give the boundaries in between. A user can find the real number. So you could also ask, so what are these uncertainty measures? What are these? And these can be anything a statistician can think of. So the often encountered confidence intervals or measurement uncertainty measures are confidence intervals, Bayesian credible intervals, prediction intervals. So the frequentist confidence interval is most known in statistics, but the Bayesian credible intervals is the result of a Bayesian analysis. And the prediction interval is the result of doing a prediction. Now, for statisticians, these different types are really important because you would like to know what kind of analysis was done. However, for communication purposes in general, this is not really an issue because it's more of a statistical detail. So the measurement expresses the confidence that the Official Statistics Institute has in this number. So are there questions in between?
So for those who just joined us, I saw that we have an increase in the number of participants. So for ask questions, you can use the chat. And then, of course, otherwise, we will also have the final discussion after the next set of slides. But if you have any questions now, please. So it seems that we have no questions.
Okay.
So I suggest that, yeah, we go, oh, no, now we have, of course. So do you have some example of prediction interval?
Not in my slides, but for example, in Statistics Netherlands, we also produce the population predictions. And for example, the prediction for 2060, and for the Netherlands, it runs from so the 95% prediction interval runs from 12 million to 24 million. So that's really a wide interval for 2060. So in official statistics, most of the cases we publish statistics on the past or the current, not on the future, but in some cases we do.
Okay. Oh, yeah, please. No, okay, we can go on with the other question that we have. So for the question of the slides are already available on the EMOS 2020 events website, and I will indicate the link again here in the chat. But before, I would like to read the second question for our speakers. So the matter is statistical literacy of the audience. Am I right?
Yes, but the next slides will go into this a bit more. So the short answer to the question is it matters when people know about statistics, but most other people do have a notion of what uncertainty is. Not an exact notion, but they are not afraid of it and they know how to deal with it.
Yeah, but I suggest maybe we can go on this.
Yeah.
Yeah, so we proceed. Thank you.
So the third method is visual communication, which is quite a powerful method. Data visualization helps to detect patterns in your data. So it's a very important communication channel. If you look on the websites of visual statistics, you can see all kinds of visualization examples of statistics, and of course our previous slides, so the slides with my two examples, are also visual, and they immediately show what's happening with the data. So visualization can, so if I would have presented these numbers into a tabular form, it would be quite difficult to see what was happening. Right now you can immediately see what's happening for the different age groups, and that the accuracy for the data is, or the measurement actually is reached with the older age groups. So data visualization is quite powerful. So it could also be used because it can summarize large quantities of information, and it may encode uncertainty. So that's a powerful tool, so we should look into this. So I recall the previous slide, so why are official statistical officers so prudent or careful for publishing statistics? So one of the two of the reasons could be that users don't understand uncertainty measures or they don't need them. So let's look into these two reasons. So luckily there are two user studies. So one, or at least two user studies that I'm aware of. So one user study is the perception of visual uncertainty representation by non-experts. So this user study looked into how do lay persons, so people who are not accustomed to statistics or uncertainty, how do they perceive uncertainty measures or the visual representation of uncertainty measures. So they did a user experiment with 140 users, and they tested how users can read uncertainty from a graph. And the users were asked, so given a number, how certain is that value? And I used different visualizations for that, so which I will show in later slides. So one of the nice things is that, so laypersons, or most people, are used to weather predictions. And weather predictions do a very good job in educating the people in uncertainty. So many people are aware that what the weather person tells us that the weather will be next day is not that certain, and that and what the next week will be is even less certain. And weather predictions often encode uncertainty in uncertainty bands around line graphs, as you can see. So this was one of the things they tried to test. So they did this for different chart types. So they had some numbers, and their users had to read off the values from these graphs. And they used these different types of graphs. So the first one is just a solid border. So this assumes that there's an interval, so it could be a confidence interval or a Bayesian credible interval or whatever. So there's a point estimate in the middle, and there's a boundary around it. They also used a dashed border. They used a band, so C. They used a gradient, D. So a gradient is more than you say something about the distribution of the value. So not only that it is in between these bands, or very likely in between these bands, but also how it's distributed within these lines. They used also two different variants with thinning lines, and so E. The F is also quite interesting. They used random lines. F has also two different names because it was invented not only by them but also by two different people, or at least two different people. It's also called a spaghetti plot because it resembles a bit of a spaghetti. And it's also a hypothetical outcome plot, which is a more nice name. And what it does, it shows different versions of, random versions of what it could have been. And last but not least is the error bar. So they tested all these types of plots, and what they found is that most people can just So non-experts can read these probability intervals. So users with high numeracy or statistical literacy are better at it. That's because they had some education in this. But non-experts can also read these kind of intervals. They have a notion what they mean. And they had no significant difference in response time. So the argument that users cannot use them or are not cannot read them is not correct. The other nice thing is the random lines or spaghetti plots or hypothetical outcome plots. They work well for stochastic numbers. So people are aware that these could also be different, that the process is a random process and the outcome could have been different than what it is. Another user study was about the effect of displaying uncertainty in line and bar charts. I was involved in this, and we did a user study with 110 persons. And instead of reading the uncertainty, the task was a bit different. We asked two things. So in a line chart, so how does uncertainty affect the overall trend? So could users read a line chart better if uncertainty was displayed or not? And the other thing was in bar charts, how does uncertainty affect comparing two values? Because that's a typical thing when you're using bar charts. And we restricted to users. We assumed there was a confidence interval and what that meant for the interpretation of the facts. So we did this user test with synthetic data and put in some effects. And this data showed that when the confidence intervals were shown, so when the uncertainty measures were shown, the user statements were more correct. So it improved the statistical statements made by the users. And that was mainly because some random noise was filtered out. Because some users thought that when there was some random noise effect in the data, they thought it was a real effect. And when showing uncertainty bands or measures, it worked better. We tested different measurement types. So again, the band, again, the error bars, and without point and with point estimate. And for line charts, we had the following results. So displaying uncertainty improved the user statements, so they were more correct. So band with line, so an area around the line works best for point estimates. And if you have just an interval estimate, an error bar works better. And best of all, users did not freak out on uncertainty, so they find it a very natural question we were asking, and they really appreciated it. And they started asking, so what does this uncertainty measurement mean? So what's the definition? And I think that was a good thing. So that we made them curious what the uncertainty measure was. So I'm skipping these two. So error bars, we did also some tests, and we did also some variance on the error bar. So the problem with error bars, if you look into visualization literature, it's quite well known that error bars work, but they're not really well designed because they're visually a bit asymmetric. So the upper part and the lower part of the error bar are not equally visible. So we tried to do some tests with other versions. So we had a chisel version and a cigarette version, and the last two worked a bit better than the normal error bar. So bar charts displaying uncertainty makes users less confident in comparison tasks, which is a good thing because there's statistically less difference. There was no really significant difference between the different visualization methods. And the other nice thing is that people who had a PhD preferred the error bar, but it did not perform better than the other methods. So that was more an education or a preference effect. So all these methods we saw until now used an interval, an uncertainty interval. But if you use a bit of an advanced statistical method, you end up with a probability distribution instead of an interval. And you could use one of the following graphical methods. So instead of just an interval and a point estimate, you will have a distribution of values. Okay. Going back, sorry. So for example, and this is an example from May in 2019. The author May, I mean. So these are 5 different ways of showing a distribution of values. So one very well is known as the density plot, which is used by statisticians quite a lot. A more recent version is the Weiden plot, which just is essentially the same as a density plot, but just mirrored in the x-axis, in this case. You often encounter a gradient plot, which encodes the same information, but then with the color more or less filled with white, for example. So that's the same information, but displayed differently. And the last two are really statistical. They seem a bit far-fetched, but there's a nice twist to this. So the fourth is the cumulative distribution function, the CDF, which is well known to statisticians, but not to the general public, I guess. And even less known is the complementary CDF, or the CCDDF, which is the inverse of the CDF. Well, the last two seem a bit strange to use in communication, but what you could do is you could rotate the last one, so the complementary CDF, and you get a graph like this. So each bar is a CCDF, and it shows the US unemployment over time. And in this case, the blue color encodes the measured values or the estimations. So you can see from the bars that they start at a certain value and they end up in the upper range. And the red colors encode the predictions. So this is a nice combination where they use the distribution as a result from their statistical analysis in blue. So the uncertainty what the employment was. And in red, the prediction error. So the uncertainty what the employment will be in 1, 2, or 3 months. In this case, you can see the uncertainty is increasing quite a lot. So this is a nice example where they combine both prediction and estimation error, and they use the distribution of their method. So it's good to know that there is a project going on right now. It's called Communicus. It's a Eurostat project. Its goal is guidelines in communicating uncertain knowledge in official statistics. It has several tasks. So one of the tasks is to describe the possible sources of uncertainty. So where does uncertainty in official statistics come from? Also methods for calculating these uncertainty measures, visualization guidelines, and there's also a proof of concept done using these 3 parts on scanner data. And the reports will be available on the Eurostat website, so that's good to know. The project runs until half June, I guess. Yeah. And I'm part of the project. So my advice is that start publishing uncertainty measures and plot them. Users appreciate it, and official statistics is statistics, so we should show the uncertainty in our data. This is a quote from Tucky, a well-known statistician from the previous century. It's far better an approximate answer to the right question, which is often fake, than an exact answer to the wrong question, which can always be made precise. So the floor is open to the final questions or discussions.
Yes, thank you, Edwin. So participants, so this is the time for the final discussion. If you have questions on the last part of the presentation in general, on the communication of uncertainty, please, you can use the chat. See. Okay, so we have a question. Have you done more testing in the Eurostat project?
It's a good question. Not yet. We are planning to do so, but not yet.
Okay, and then another, I really like the CCDF plot. Thank you. Are there already study results about user perception of these plots?
They are testing it. So the CCDF were not invented by me, but by Matthew Kay, and they are testing it. But I'm not sure if they are published yet. Yeah.
Okay, and then it is not easy to pose the right question unless the official statistics helps in it. Okay. And then how to plot the rank of estimates with how to plot the rank of estimates with uncertainty.
Oh, that's a good question. I don't have a good answer to this question yet. Yeah.
Yeah, because I think I was also thinking that this is a crucial point, because we of course sometimes ranks are produced, but then of course usually I think, okay, but they're not taking into account directly the uncertainty in that. So maybe in the ranks that's crucial, because of course if, for example, we derive the confidence interval, if they overlap, so maybe sure. So that's, I think
it's a really good question. I'm not aware of any plotting method for doing this, but I will look into it. Yeah. Good question. Thanks.
It's a challenge.
And a challenge. Yeah.
Yeah. Did you check the willingness to see uncertainty in official statistics broken by field of work of the users? Okay, so maybe you think if people that are users that should be, maybe this should be addressed in different ways. Maybe you think.
Well, what we did is we did also a small survey on our direct users, so from policymakers and from more statistical literate users, and they really liked that they had access to uncertainty measures. I'm not sure if that answers the question, but
see uncertainty in GDP is different than seen uncertainty in other economical indicators, for example. Okay, so you think maybe the kind of the indicator.
Yeah, we did not test this. It's really it's again a good question. We did not test it yet, but we should. Yeah, but it's more about the political impact.
Yeah.
Yeah.
Yeah. So you didn't ask also to, I mean, decision makers, politicians. You have any feedback on this, on the perception of uncertainty?
Not yet. No.
Okay.
We're planning to do this.
Yeah. Okay. Very interesting.
Yeah.
Okay. So any other questions? Otherwise, we can conclude. Let's see. No, so already thanking you. So I will just join them. So thank you, Edwin, for this very interesting presentation. And many thanks, of course, also to our participants who join us today from many different places. So as we already said, you can already download the presentation from the EMOS 2020 events website. The link was also made available on this chat. And the recording of the webinar will also be available as soon as possible on the same website. And there you can also find the recording of the first 5 webinars of the EMOS series of webinars. So now, in the meantime, I will ask you to check the inbox of the email account that you use for registering to the webinar, as you have already received the link to a search survey about today's webinar. We really appreciate your feedback to further improve our webinars. The next webinar is scheduled on Wednesday, 15th of April, when Daniele Vignoli and Eleonora Melli from ISTAT, Italian National Statistical Institute, will be presenting on demographic change and official statistics. So I hope they will join us also for this webinar and for the next webinars. Thank you very much to everybody, to Edwin again, and have a nice evening. Bye-bye.
You too.
Bye.